Alright, for the record, let's just say my name is Mr. Jensen. And I'm here today to talk to you a little bit about solutions. There's enough there to contain that. However, before we get into solutions, what you're seeing here before you is a reaction of two different solutions that are mixed together to form this chemical reaction. We will get into exactly what this chemical reaction is a little bit later. But for now, let's talk about safety. First and foremost, quick change of my glasses here. All right. So, when dealing with any kind of chemicals or any kind of volatile substance, you want to be aware of, hang on, my little slight technical difficulty. You want to be, thank you, Mrs. Jensen. You want to be aware of safety. The solution demonstrated here today is made of safe handling ingredients, so precautions really aren't necessary outside gloves and probably some goggles, but for the most part it's not very volatile and it's not really going to explode in your face. However, that's not true for all chemicals. That being the case, next slide. Wait, it's working now. For every chemical or anything that you might be using in the professional world, they need to make available to you at your job the safety data sheets. Safety data sheet should be for any and every single chemical that you use, and the safety data sheet is going to contain at least these 10 things I have listed here. So first one is, what is the emergency phone number? In most cases it's going to be 911. What is the substance recommended for and how is it supposed to be used? Are you using it correctly? How dangerous is the substance? You need to know if this is something that you need a lot of precautions for. You need to be in well-ventilated areas. What protective equipment is required when working with substances? And again, all this is defined. Is there any precautions that you should be aware of? Precautions being like, do you need to work under a flow hood, which is a hood that is going to suck up any vapors or anything. So. Or do you need to work with gloves inside? There's all kinds of precautions that you need to be aware of and know what you're working on. How do you clean up the substance if it spills? We almost had to deal with that right here, but it looks like I've reached the saturation point of my my reaction, so I think we're going to be safe. It looks like I've had just enough containment. So what should you do if the substance gets on your eyes or skin? Again, there are some substances that are really bad. If you're working with hydrofluoric acid, for instance, you need to go and seek a hospital immediately. Or hydrofluoric, yes, HF. Bad stuff. What should the substance look like? If you think you're working with one substance, you need to know what it looks like, because if it looks like something different, or if you're working with something different and you don't know what it is, that's really bad. So always know what the substance should look like, and again, the safety data sheet is going to tell you that. And what you should not mix with the substance. Everybody knows about bleach and ammonia when making a cleaner, so as a for instance. And what are the effects of the long-term exposure? That is really important to know, because if you are working around something that's creating a gas or something, then you need to know if you start to feel lightheaded, or people around you start to feel lightheaded, or have any kind of reactions. It could also be runny nose, it could be headaches, it could be, who knows, you could even start to get rashes. So anyway, you really need to know what the effects of long-term exposures are. So, with that, wrong way, let's go to what is a solution? That's what we're here for today. A solution, very simply put, is a solute that is dissolved inside of a solvent. As a preview, the reaction that you witnessed was actually two different solutions combined to demonstrate what we call a decomposition reaction. So together they didn't exactly make a solution, but I did use two different solutions to create that reaction. But we'll get into that more later. So, what are the components of a solution? Darn it, wrong way. I'll get this down, don't worry. I got at least another 10 minutes. The components of a solution, you have your solvent, and your solvent is the most abundant component in a solution. So the solute is the other component, and that is the component being dissolved in the solution. And in this case, today, since we're dealing with something that's more of water, I can never pronounce this word, so I have my lovely daughter running the camera who can tell me. Isabel.
It's an aqueous solution, which is a solid, liquid, or gas that can be dissolved in water.
All right, she's only a sophomore, everybody. Good job, Isabel. Thank you. All right, so today we're going to be dealing with an aqueous solution.
See, you got it.
All right, go Dad. Yeah, so let's go on. There are 9 different types of solutions, and of those types of solutions, as you can see here, every state of liquid takes it, or every state of matter takes its turn being either the solute or the solvent. So in the case of gas, you've got your gas-liquid solution, which would be soda pop. You've got your gas-solid solution, which would be charcoal filters used for filtering different gases and stuff. You've also got your gas-gas, which is your basic air that you breathe every day. You've got your liquid-solid solutions, which are amalgam fillings, which most of you probably haven't experienced because I think they've replaced them with better materials. So anyway, had my fair share. Be glad you don't. You've got your liquid and gas, which is humidity, so water vapor in the air and stuff is also a solution. You've got your liquid, which is like vinegar. And here you can see it's acetic acid and water. Then you've got your solid gas solutions, which are like fire extinguishers used for putting out chemicals. You've got solid liquid, which is ocean salt water, and that we'll actually be taking a closer look at. And you've got your solid, which is pretty much any kind of a metal alloy that you work with, or pretty much any metal that you see. So in this case, I'm using brass as an example, which is zinc and copper. So that covers that. So a general rule for solutions is what they call like dissolves like. And what that means is that deals with the polarization of the molecules themselves, and if you have positive and negative polarization, and if you have 2 positive and negative polarized molecules, then they're likely to dissolve each other. In this next example, we are looking at salt water. Here, this is water dissolving salt, and this is found on page 226 of your textbook, and what you see here is the molecules of the water. Not sure if you can see my pointer or not, but here on the outside of this you've got the water surrounding the molecules of the salt, and what happens is the positively charged hydrogen molecules of the water are going to be attracted to the negatively charged chloride of the salt, and it's going to break it off. That's what that's demonstrating right there. And then the negative charged oxygen molecule is going to be attracted to the positively charged sodium, and that's going to reach in there and that's going to break that off. So, and that is going to be what breaks down the actual solid of the salt. So you've got your liquid solvent, which is the water, obviously, and it's going to break down the salt. However, since obviously solids are a little bit more structurally rigid, if you will, that's where we're going to get into the water molecule. I'm going back. All right, so as you can see, the water molecules is basically taking 8 molecules to break down just one, to create one of the negative salt ion and a positive salt ion. Eventually what's going to happen is there will be no more solvent molecules to dissolve, and the solute molecules, and your solution has reached what they call saturation. Let's see if I can go the right way. Yeah, darn it. Okay, there we go. Saturation. So, saturation is defined as the solute's dissolving limit. So the solute has dissolved everything that it can, and it can't possibly dissolve anymore. When dissolving a solid, a liquid, dissolving a solid into a liquid, temperature is important. As the solid is heated up and the molecules become more excited, the molecules of the solid become more excited, it's easier for the solvent to break them down, because obviously there's more space in between them and it's easier for them to break down. And how much easier it is depends on the solubility of the substance. Now, solubility is the next term, and that is defined as the concentration of solid solute in a saturated concentration at a given temperature. This next slide is going to show, all right, the next slide is going to show an example of that. So now you can see here that you've got temperature across the bottom. So you go all the way up to, well, in this case it goes all the way up to 100 degrees. But over here you have grams of salt in liters of water. So what this is saying is that at 60 degrees, you can basically dissolve 370 grams of salt in 1 liter of water. And again, it decreases as the temperature decreases, because it's much more difficult for the water to break down the solution. Does anybody have any questions on this?
So if you add more water...
Yes, Mrs. Jensen, please.
So if you add more water, could you dissolve more salt?
Yes, I do believe that would be the case. You would, because you're adding more of a solvent. So if you have more solvent, you have more available molecules, and having more available molecules, you should be able to break down more once you've reached your saturation limit. So yeah, so 2 liters of water should break down more salt than I would assume it'd be roughly exponential. So, any more questions? Smart daughter, I'm looking at you. All right, no questions there. All right, so we will be looking at the natural breakdown of, right now for this experiment and what you have here, we'll be looking down at the, with the elephant toothpaste. With the elephant toothpaste, we will be looking at the natural breakdown of hydrogen peroxide, the hydrogen peroxide molecule, into hydrogen and water. So here's hydrogen peroxide, where you've got two hydrogen, 2 oxygen, and over here it's going to naturally break down to where you have 2 water molecules, and it ejects one oxygen molecule. However, left to its own devices, this chemical reaction takes way too long. So, through better chemistry, we are going to help it along. And in order to do that, we are going to use elephant toothpaste. And for this demonstration, we'll be taking a look at 2 different solutions. As I mentioned earlier, it's 2 different solutions mixed together to create, that will create a decomposition reaction that results in a lot of foam and some water. So, without any further ado, all right, so here is the solution of the elephant toothpaste. So you've got hydrogen peroxide, which is providing the molecules to be broken down. And then the solute is going to be the dish soap. So that's going to be the first one. That'll be the dish soap, and that stabilizes the escaping O2 gas and to make the visible bubbles, as you can see here. So all of that was the hydrogen peroxide breaking down and the bubbles being created. And then the second one is going to be the water and the dry yeast, which the water dissolves the yeast and makes it more readily to mix with the hydrogen peroxide. And the yeast itself, as we found out in our class, when we mixed the hydrogen peroxide and the yeast, we had the exothermic reaction, and we're looking for that reaction, and that reaction is actually going to accelerate the breaking down of the molecules. So with elephant toothpaste, what you're looking at is the hydrogen peroxide molecule rapidly being broken down and the dish soap capturing the air that's escaping and creating the bubbles. So, all right, my final slide before we get to this demonstration. Let me set that one aside. Just so happens, I got another one here. I'm really gonna hope this is big enough. It might not be. All right, so I have a pre-mixture here of yeast and water. I'm hoping the yeast is still active. In a couple of these experiments, I kind of killed the yeast. It actually needs to be alive, but killed it mixing it too early. No jokes, please. And hopefully this is going to work. If not, we might need to pause this recording for just a second. So, all right. So first, you're going to need a bottle.
Do you need any safety precautions, Mr. Jensen?
Thank you, Mrs. Jensen. I appreciate that. I was just so excited to get this underway, I completely forgot. However, Kimberly Clark to the rescue with the gloves. And shit. All right, enough. Peanut gallery. Silence. All right. Here we go. So, Kimberly Clark, high quality, never break, never leave you high and dry. There we go. All right. I got my gloves.
There's nice big gloves.
All right. I don't need these. I'm not quite as blind as... Okay, I'm blind, but still, nonetheless, I'm going to hope that I can do it with these safety glasses, because the safety glasses are a little bit more safety. They protect the sides, they protect the fronts. So, am I good to go?
I think so.
All right. Do you
Yes,
feel
yes,
safe? Are you
please.
at a safe distance?
I am.
All right. Isabel, you at a safe distance?
Yes.
All right. Excellent. So first, I have my hydrogen peroxide. Slightly better than the stuff you get in the stores. This is actually 12% hydrogen peroxide, and let's hope to get a little bit better of a reaction out of this. So, I'm going to add some hydrogen peroxide. Precise mixture. Going to add a little bit of dish soap, and this is going to be my first solution. All right, so there's the first solution. I'm going to get anything electronic out of here and get my glasses out of here, because if it does overflow, I need to know how to clean this up. All right, and now, thank you, dear loving daughter, I'm going to put a little bit of food dye in here. That just kind of makes it a little bit more exciting and, well, colorful. So I'm adding that to the solution. Doesn't necessarily need to be there, but like I said, makes it a little bit more colorful. So now that we've got that, I'm going to stand back. I've got my yeast and my water mixture here. I'm going to add them together, and I am going to hope for the best. And there we go. Whoa, Nelly, look at that. All right. And that is our reaction. Like I said, here, I haven't gone over the slide yet, have I? Okay, excellent. Now, as this is happening and you're getting this, let me go over the slide. What you're seeing, the yeast is mixed with the warm water to make a solid liquid solution, which is what we covered. So you've got the warm water breaking down the yeast, the solid, so it mixes up. Then you've got the, whoa, damn, I can't read that. Let me take my glasses off. All right. I can see. Okay, so hydrogen peroxide is mixed with dish soap, and that creates the liquid on liquid solution. I hope that doesn't overflow. That creates the liquid on liquid solution. When the two components are combined, the yeast is catalyzing with the hydrogen peroxide, causing an exothermic reaction. The exothermic reaction accelerates the decomposition of the hydrogen peroxide, causing a rapid release of the oxygen gas. That'll be the bubbles that you're seeing. The soap is capturing the escaping oxygen gas and stabilizing it, creating the foam you see. As it continues to, oh Lord, as it continues to break down, the foam is pushed out of the bottle which continues until the decomposition is complete. And there is only water left in the bottle and all the oxygen has been released. Okay. I do believe that completes this demonstration. Isabel, do you have any questions?
I do not.
Are you sure?
Reach the point of saturation?
No.
How do you know?
Well, it's slowing down, which is a good thing. However, it's still coming out of the bottle. So as long as it's coming out of the bottle, it is still breaking down and the reaction is still going on. So it will stop as this one did. And really, this one I actually had a pretty good mixture, and there's just a little bit. What you have left there is actually just water. So, all right. If there are no more questions, I will be posting this, and please, anybody that happens to be watching this, by all means, post the questions in the discussion, and I will do my best to answer them. And for now, thank you for tuning in, and until next time, adieu.